Yes, any doubts from the last class? Abdullah. So up to last class, we have completed potential energy due to a dipole. We did all types of capacitors. We did parallel plate capacitor, cases of parallel plate capacitor. Then we did spherical capacitor. We also computed energy storage, right? So let's do some numericals based on these expressions. Then we will start electrical circuits. So the first question that's given in NCERT based on these expressions is, NCERT says calculate force between the plates of capacitor. Force between the plates of capacitor. So you have two plates of capacitor, one plate here, another plate. One plate is positively charged. Positively charged. Another plate is negatively charged. You're supposed to calculate the separation, the force between the plates. The separation between them is. Amalia, can you calculate the force between the plates? Charge density of the first plate is plus sigma, second is minus sigma. Yes, Amalia, what's the force between the plates? So Amalia have stopped responding. Mariam, what's the force between them? Mariam. No answer from Mariam also. Noor, can you calculate the force between these two plates?
So electric field into charge.
Yes. Can we write this force in this way? Can we write that the force between the charges is KQQ by R D square? Yes, Ahmed. Ahmed, can I write the force between the two plates as KQQ by D square? I know you were absent for a very long time, but you have done Coulomb's law.
So is the K constant?
Yeah, K constant.
Is the...
Can I use Coulomb's law?
Yes, you can do that.
No, I can't use Coulomb's law. Abdullah,
but here it is like positive and negative charges are there, right?
No. Abdullah, why can't I use Coulomb's law here?
Oh, because Coulomb's law is for point charges.
Yeah, Coulomb's law is for point charges. You have two plates. You cannot use Coulomb's law here. So as Noor said, we won't use Coulomb's law. What we will do is, we will take the field due to one plate, E, electric field due to positive. Electric field due to positive. So I can't use Coulomb's law to calculate this force. So I will use the expression of field. So field due to the positive plate is sigma over 2 epsilon. Sigma I can write as charge upon area. So I can write that the expression of field is Q by A into 2 epsilon. That's the electric field. That's first equation. So in this electric field, we place a negative charge. So this field will exert force on this negative charge. So next what we can do is we can calculate force on minus Q due to field. Force on minus Q due to electric. We can write that force in this way, like F is equal to minus of Q. We can write that force as F is equal to minus Q, then put the expression of field. It's Q over A into 2 epsilon. So force will be minus of Q square over 2A epsilon. This negative sign shows that the direction of force is opposite to that of field. So remember, you can use Coulomb's law only if both the charges are point charges. If you don't have point charges, then this expression is very, very useful. F is equal to QE. Calculate field due to one charge. and then multiply the second charge with that field and you will get force minus q square by 2a epsilon. Is it clear? Amalia, Mariam?
Yes, sir.
Just note it down. Shahzada and Ahmed. Shahzada was not present in the last class. Even Ahmed was not present for a very long time. You both can have to wait just for 5 to 10 minutes. After 10-15 minutes, I will start circuits. So circuits is an independent topic.
Okay, sir.
When we do circuit, we will do circuits of chapter number 2 and 3 together. Like we'll do capacitance and resistor together. Tell me if you have written. I will erase it.
Done, sir.
Written. Amalia, can I change the slide?
No, sir.
Okay, so now we have force between the charges. Next is we need density, energy density. Next question says calculate energy density between the plates of capacitor. We need energy density between the plates of capacitor. When we say energy density simply means energy divided by the volume of the system. It's energy per unit volume. So we can write energy density as energy density. We represent energy density by small e. This energy density is energy divided by the volume. This is the expression of energy density. It's energy by volume. So we can write energy as half. We can use, like, let me draw the parallel plate capacitor first. See, this is your capacitor. This is your parallel plate capacitor. So area of each plate is A, and separation between the plates is D. The energy stored in the capacitor, I will represent energy with capital U and will represent volume by V. So energy stored in capacitor, one expression is this, half Q square over C. That's equation number 2. I call this as equation number 1. When I calculate volume, then volume is area multiplied by separation. It's A multiplied by D. That is equation number 3. Now we can substitute both energy as well as volume in equation number 1. We can substitute 2 and 3 in 1. When we substitute 2 and 3 in 1, the energy density becomes energy, which is half. It's Q square by C multiplied by volume. That's A into D. Next, we can write capacitance as this is half. It's Q square by C, which is epsilon naught A by D. Like I'm using the expression of capacitance, epsilon naught A by D, parallel plate capacitor multiplied by D. This D will cancel this D. So the energy density, expression of energy density is, there is one more A. This capacitance, see, the formula of capacitance is epsilon naught A by D. This we derived in the last class. So this is A into D only. This D will cancel this D. So energy density is half. It's Q square over A square into epsilon. We can write Q by A as sigma, charge by area as sigma. So we can say that energy density is half sigma square over epsilon. We can multiply denominator and numerator with epsilon naught. So we will get energy density is half sigma square by epsilon naught square into epsilon. Next, we can write sigma over epsilon naught as E. This is the expression of electric field between the plates. This is E, electric field between plates. Electric field between plates. We have derived this in the last class. So when I substitute, instead of sigma by epsilon naught, if I substitute E, then I will get that energy density is half E square into epsilon. This is the required expression. The energy density of a parallel plate capacitor is half E square into epsilon. Okay, just note it down. This is the energy density of a capacitor, means energy per unit volume stored in the capacitor. Just let me know once you have written. I'll change the slide. Yes, can I change the slide now?
Yes, sir.
Okay. Mariam?
Yes, sir.
This is energy density for a capacitor. See, the energy density depending upon electric field only. See, half is a constant, epsilon naught is a constant. This shows that energy between the plates of capacitor depends upon electric field. If you change electric field, then the expression of energy will change. So this shows that energy between plates of capacitor depends on electric field. In fact, energy is stored within the electric field. In fact, energy is stored in field. Energy stored in electric field. We have derived this expression particularly for a parallel plate capacitor, because for parallel plate capacitor, these calculations are straightforward. These are straightforward calculations for a parallel plate capacitor. But if you take any other type of capacitor, spherical capacitor, or any other case, like if you have field in a region, in your room also, if you have some electric field, and you take unit volume of your room, means 1 meter cube volume of your room. In your room, you place a point charge or some charge body. That charge body will generate some electric field. You consider a 1 meter cube volume of your room. This 1 meter cube volume, which have electric field E, have this much of energy. So this energy is not confined to capacitor especially. This is confined to field. If you have field inside a capacitor, then you will have energy. If instead of capacitor, this field is in space, then you have energy in space. So this is energy of electric field. Note it down. Yes, written, noted.
Yes, sir.
Yes.
Okay. So in the last class, we did parallel plate capacitor. We have calculated various cases for a parallel plate capacitor. Capacitance of a parallel plate. We have calculated C is epsilon naught A by D if air is in between the plates. We wrote that C is K times epsilon naught A by D if some dielectric constant in between the plates. We wrote C is epsilon naught A by D minus T 1 minus 1 by 2. Or we can write that C is epsilon naught A by D minus. This is when air is between the plates. This when the whole space is filled with a dielectric. This when the dielectric is partially filled. And this when you have a conducting slab between the plates. So I'm giving you a question. And we had three expressions for calculating energy also. A parallel plate capacitor with plate area (10 centimeters square) and separation 5 mm have a plate, dielectric plate of 3 mm. Its dielectric constant is K equal to, let's say, calculate first part. Capacitance. Second part. Charge stored and energy if it is connected to a cell of 100. So first of all, you have to decide for parallel plate capacitor in this numerical which case is given. When the air is in between the plates, dielectric slab is fully filled, dielectric slab is partially filled, or a conducting slab. So Mariam, which case is this? The case given in the question is which case? Air in between the plates, dielectric slab fully filled, partially filled, or conductor?
Sir, partially filled.
Yes. Right, Mariam?
Yes, sir.
Why is it partially filled, not fully filled? Why is saying that the slab is partially filled?
Because it has this the constant dielectric constant, and also it is separated by the distance.
But dielectric constant, if you have dielectric constant, then you can write this formula also. No? But slab is, I'm just asking this thing, this simple thing. This is your parallel plate capacitor. This is one plate. This is another plate. You have a slab. I'm asking you to decide whether the slab fills the whole space in this way, the whole space between the plates of the capacitor, or this filled the space partially in this way. This you have to decide, which is the case. Yes, Mike. Abdullah said this is case of partially filled. The dielectric slab is partially filled. Can you decide why he said that this is partially filled? No. People are not revising. Huh? See. Mariam, just read the question and tell me what's the separation between the two plates of the capacitor?
5 millimeter.
5 millimeter. And what is the thickness of the slab?
It is 10. Oh, sorry, 3.
3 mm. So this 3 mm slab cannot fill the whole space. To fill the whole space, you need a slab of 5 mm, right? This is partially filled. This is partially filled. Dielectric constant is 2. This is the case. Do this calculation. Get the value of capacitance. And then I also need charge and energy stored to it. After this, we'll start sharing of capacitor or sharing of conductor. I have a chance. Answers. Capacitor is a very important topic. If you need any help in calculation, just let me know. This is the formula that you will be using. Okay, Abdullah. You can do one thing. You can calculate in terms of epsilon naught if you want. If you think that substituting epsilon naught will make your calculations lengthy, you can do your calculation in terms of epsilon naught. I have to check, Abdullah. I just have to check. Meanwhile, start calculating your charge and energy. See, the expression of capacitance is C is epsilon naught A over D minus T 1 minus 1 by K. You just have to substitute these values. When I write A, area, how much is the area? It's 10 centimeters square. 10 centimeters square. So that's 10 into 10 raised to the power minus 4 meters square. If I want separation D, D is 5 mm. So it comes out to be 10 raised to the power minus 3 meters square. Separation is 5 mm. It's 5 mm. Means 5 into 10 raised to the power minus 3 meter. T is 2 mm. 2 or 3 mm? 3 mm. So it's 3 into 10 raised to the power minus 3 meter. Dielectric constant is 2. When I substitute all these values here, I get C is epsilon naught, which is 8.85 into 10 raised to the power minus 12. Area, which is 10 raised to the power minus 3. Divided by D, which is 5 into 10 raised to the power minus 3. Minus T, which is 3 into 10 raised to the power minus 3. 1 minus 1 by K, 1 minus 1 by. See, when you try to solve it, this is 8.85 into 10 raised power minus 12 into 10 raised to the power minus 3. See, from these two terms, you can take this 10 raised power minus 3 as common. When you take 10 raised to the power minus 3 as common, you are left with 5 minus 3. 1 minus 1 by half is half into half. So capacitance is 8. This 10 raised power minus 3 will cancel this term. It's 8.85 into 10 raised to the power minus 12. That's 1.5. So it's 3.5. This much of fat. This is your capacitance. That's the first part. The second part of the question. So, Amalia, you were in the last class. Do you remember if you have capacity, how will you calculate charge? Relation between charge and capacitance, Amalia. She don't remember. Noor. Yes, Amalia is telling. Wait. Yes, Amalia. Relation between charge and potential.
Sir, I'm not sure.
I'm sure. Okay, Noor. Relation between charge and potential?
So C is equal to Q by V.
Q is equal to C. Potential is given in the question. It is given that potential here is 100 volt. So V is equal to 100 volt. When we substitute values here, then Q is 8.85 divided by 3.5 into 10 raised to minus 12 into 100. So we get Q is 8.85 divided by 3.5 into 10 raised to the power minus 12. That's the charge. Okay, Mariam, remember any formula for energy stored in capacitor? Yes, Mariam. How will you calculate energy stored in the capacitor? Ahmed, sorry, not Ahmed. Abdullah. Formula for energy stored in capacitor.
Sir, QV by 2.
Yes, or yes, we can use various formulas. Like we can use half CV square, or as Abdullah said, we can use half QV, or we can use half Q square plus C, whatever you prefer. This is how we calculate energy stored in a capacitor. Note it down. Sure. Okay, you can take break of 7 minutes, 5 to 7 minutes, then we will start. I think it's namaz time there. No? We can have a break of 7 minutes, then we will start. We'll start at 9, 12, 9, 11.
Okay, sir. Thank you, sir.
Okay, Ahmed. Yes, shall we start? Abdullah. Okay. See, for the next type of questions, the next type of questions that you may get in capacitors are conceptual questions, basically. So I'm writing various conceptual questions in the form of table. So you have a parallel plate capacitor. You have two plates. Area of one plate is A. The area of another plate is also A. And the separation between the plates is D. And we connected this capacitor. Okay, no issue, Mariam. We connected it to a cell and the potential difference of the cell is D. So this is a parallel plate capacitor. Parallel plate capacitor. With air between plates. With air between plates. And connected to cell of potential difference. First of all, I need the formula for capacitance. We take a capacitor, we connect this capacitor to a battery of voltage V. When the air is between the plates, the medium between the plates is air, then the capacitance will be epsilon naught A by. Second, you should remember the formula to calculate charge. The charge between stored in the plate of capacitor is C naught multiplied by the potential difference, that's V naught. Third, I can write the potential difference. Potential difference between the plates is V naught. Fourth, we can calculate electric field between the plates. Electric field is potential difference divided by the separation between the plates of capacitor. And the last is the energy stored. Fifth one. The energy stored between the plates of capacitor is usually half C naught V naught square. See, these are 5 different conceptual questions. Usually this data is given, like capacity, you know that capacity of a parallel plate capacitor with air between the plates is epsilon naught A by D. Potential difference is the potential difference of the cell. Charge stored is C naught V naught. Electric field is potential difference divided by separation. And energy stored is half C naught V naught square. This is the given condition. Now, in the numerical, you may be asked to calculate the capacity when the plates between plates of the capacitor are filled with a dielectric of dielectric constant. With a dielectric of dielectric constant K. This is potential differences P naught. Battery remains connected, but you fill the space between the capacitors with a dielectric of dielectric constant K. So now battery remains connected. Battery remains connected. See, these are important conceptual questions. Battery remains connected and space is filled with dielectric. Since your exam will be, if your exam is MCQ type, then you have very strong chances to get questions from these 5 topics. Dielectric. So you can write your capacity is C. When you introduce a dielectric, then capacitance becomes K epsilon naught A by D. And this epsilon naught A by D is C naught. So you can write this as, this is K C naught. Means your capacity increases. So as compared to the case when the air is in between the plates of the capacitor, if you introduce a dielectric slab, then capacity will increase. Next, you can be asked what happened with the potential difference. Now, if battery remains connected, then potential difference will not change. Potential difference will remain V naught. V will be V naught. Potential difference between the plates of capacitor will remain same. It will be V naught. It will not change. If you want to calculate charge, then charge Q is equal to CV. How much is C? C is K times C naught. How much is V? V is V naught. So you can write this as it's K times C naught V naught. Compare this with this case when air is in between the plates of the capacitor. So if this, when air is in between the plates, then the charge is C naught V naught. When the dielectric is in between the plate, then this is K C naught V naught. That means your charge increases. Potential difference remains constant. If we calculate electric field, then electric field E is V by D. V is V naught. Separation D is D. V naught by D is E naught. E naught. So electric field remains constant. Next, you have to check what will happen with the energy. See, energy is half C V square. See, C is Kc naught. Your capacity becomes K times. Your V is V naught. Your voltage becomes V naught only. So it's half K times C naught V naught square. So you can write this as, this is K times half C naught V naught square. Half C naught V naught square is U naught. Huh? This is U naught. So it's Ku. So energy increases. So the conceptual question is, first question. The plates, medium between the plates of capacitor is air. What happened to capacity if you introduce a dielectric slab? Capacity increases. What happened with potential difference if battery remains connected? Potential remains same. What happened with charge? Charge increases. Electric field remains constant. Energy increases. The next question is, instead of connecting the battery, he can disconnect the battery. So this is parallel plate capacitor. This is dielectric slab. This is cell, but you disconnected the cell. You disconnect this cell. Voltage is V, dielectric constant is K. So battery is disconnected. And space is filled. And space is filled with dielectric. Now, see. Again, you have to compare this case when air is in between the plates, and you have to compare this case when dielectric is in between the plates, but you disconnected the cell, you disconnected the battery. First one. So I'm connecting here with it. Capacitance will be K times epsilon naught A by D. So capacitance will be Kc naught, which means capacity increases. So earlier you have a battery of voltage V naught and air is in between the plates. Now your battery is disconnected, but the space is filled with a dielectric of dielectric constant K. So what will happen? Capacity increases. Second, charge. Q prime. Charge will remain same. Same means the charge will remain constant as was the initial value. If initially in this case your charge was 2 coulomb, then after disconnecting the battery and reducing the dielectric, charge will remain 2 coulomb. The reason is the source of charge is cell. When you disconnected the cell, then charge on the plates of capacitor cannot increase. And we are ignoring any leakage of charge, that the charge will remain same, charge will not change. It will remain constant. So that's the difference. When the battery remains connected, then charge increases. But when you disconnect the battery, then charge remains constant. Third question. Potential difference. See, for potential difference, we can write potential difference as charge divided by capacitance. Q is equal to CV, so V is Q by C. Q prime is Q naught. C is KC naught. If you compare from here, what is Q naught by C naught? It's V naught. So we'll get V naught divided by Q. I'm saying again, I'm comparing this with this. Here V naught is Q naught by C naught. Here V prime is Q naught by KC naught, V naught by K. So potential difference decreases. If you calculate field E prime, which is V prime by K, and what is V prime? That's V naught by K. Sorry. E prime is V prime by D. What is V prime? V prime is V naught by KD. And what is V naught by K? V naught by D is E naught. So it's E naught by K. Means your electric field also decreases. If we talk about energy, U prime, it's half C prime V prime square. So it's half. What is C prime? C prime is KC naught. What is V prime? It's V naught by K square. It's half, it's KC naught. It's V naught square over K square. So the square will cancel this K. And we are left with just half C naught V naught square by. This half C naught V naught square is U naught by K. So energy also decreases. So these are 5 conceptual questions. Not 5, basically 10 conceptual questions. This will be given, and these are the 2 categories. You can say that battery remains connected, or you can say battery is disconnected. Some few of these questions are also given in NCERT. Just note it down and tell me if you still have any doubts. These are questions, these are not the part of theory. Tell me once you have written. After this, we'll start circuits. Tell me once you have written, I'll change the slide.
Said.
Yes, can I change this right now?
Yes, sir.
Okay. So this completes the theoretical part of capacitance. The next are the circuits. Okay, if you disconnect battery and the medium is here, then no quantity will change. Quantities will only change if you're introducing a dielectric.
Okay, sir.
So, Abdullah and Shazada. Now, see, these are from now onwards, this is a fresh topic. So, you must have heard about resistors. Huh? Resistors are circuit element. What resistance do in a circuit? What's the physical significance of resistance, Abdullah?
Slow down the current.
Slow down the current. It obstructs the flow of current in the circuit.
Yeah.
Just like resistor, you also have a new circuit element which is known as capacitor. This is capacitor. Just like resistor, you have a circuit element, capacitor. So, Amalia, what capacitor do? As a circuit element, what capacitor do, Amalia, in a circuit? Okay. Yes, Noor, what capacitor do in a circuit?
So it stores charges.
Capacitor store charge. So it's a circuit element which store charge. What resistor do? Resistor offers obstruction in the flow of current. So we'll be doing circuits of capacitor and resistor simultaneously. Every circuit that you can make with resistor can be repeated with capacitor. So we will not waste our time. We'll do the circuits together. Capacitor and resistor will do simultaneously. Capacitor store charge. What resistor do? It offer obstruction in the flow of current. In flow of charge. This is flow of charge that you call current. So this offer obstruction in the flow of current, which is capacitor. Second, this is the symbol of a capacitor. And this is the symbol of a resistor. Working equation for capacitor is Q is equal to CV, where Q is the charge stored in the capacitor. One plate is positively charged, another plate is negatively charged. C is known as the capacitance. We represent it by C, and V is the voltage. In resistor, current flows through the resistor and the governing equation is Ohm's law. V is equal to I. Next, energy stored in capacitor can be given as half CV square or half Q square over C or half Q. But when you take resistor, we don't calculate energy, we calculate power. Power dissipated. Power dissipated as heat. So when current passes through a resistor, then a part of electrical energy gets dissipated as heat. we are calculating that power. There are various expressions to calculate power. One is I square R, another is VI, or you can write V square by R. So this is comparison between capacitor and resistor. We'll be doing circuits of capacitor as well as resistor simultaneously. Just tell me, is there any doubt?
No, sir.
Shazada? Malia? Because these circuits will be, this topic would be lengthy. Circuits will be lengthy. In the circuit of capacitors, I will try to include almost all circuits of chapter number 3. Because if you missed from this topic onward, then you will miss your chapter number 3 also. I'm mixing chapter number 2 and 3 from onwards. Okay, just note it down and tell me once you have written.
Done, sir.
Okay. What about others? Amalia, Mariam?
Sir, can you repeat the last point of resistor?
Yeah. In resistor, when current passes through a resistor, then a part of electrical energy gets converted into heat. That's why resistors get heated up. So we are calculating that heat energy per unit time, which is known as power dissipated. Power is energy divided by time. So we're calculating power dissipated as heat when electrical energy passes through or current passes through a resistor. That's power dissipated.
Yes, sir.
Energy dissipated as heat. So Zada, can I change the slide?
Yes, sir.
Okay, the first type of questions that we get in the circuits are purely on capacitors. That's sharing of capacitor or conductor. That's the first type of questions. They are sharing of capacitor or conductor. Is what happened when we share two capacitor or when we share two conductors. Sharing of capacitor or conductor. So let's say you have two capacitors. The capacitance is C. And potential difference, this capacitor, the potential difference across the ends of the capacitor is V1. Capacitance is C1, potential difference is V1. One plate is positive, second plate is negative. Then for the second one plate is positive, another plate is negative. Capacity is C2, potential difference is V. So this first capacitor, capacity is C1, potential difference is V1. Then you have second capacitor, capacity is C2, potential difference is V2. This is before share. This is before share. Then you connected these two capacitors. When you connect two capacitors, then charge flows from one capacitor at higher potential to another capacitor at lower potential until they acquire same potential. This is C1, this is C2. Then you connect them, then charge flows until they acquire same potential. So this is after share. This is after share. So on connecting, two capacitors, charge flows from one at higher potential to lower potential until they acquire same potential. Until they acquire same potential. So after shearing, the charge is, okay, so this is before shearing and this is after shearing. When we connect two capacitors, then charge flows, but net charge remains conserved. So you can say charge before shearing. Charge before shearing is equal to charge after shearing. Charge before shearing is equal to charge after shearing. So, yes, Shehzada, what's the value of charge before shearing?
Yes, sir.
What is the value of charge before shearing? What's the charge on this capacitor, Shehzada? Capacity is C1 and voltage is V1.
So
We just
the
did the
charge will
formula
be
for charge. Yes,
CO and VO.
C1, V1. And what about the charge on this capacitor?
So it will be C2 and V2.
C2, V2. And what is charge on this capacitor after sharing?
So it will be C1 minus it.
C1V.
C1V.
And what about this second capacitor? C2V. Ahmed, what is V here?
So where
This V. What is this V?
potential, total potential,
Common potential. What is V?
common potential.
Common potential which both the capacitors have after sharing. So that's common potential V, which is C1V1 plus C2V2 by C1 plus C2. V is common potential. So I can say that V is common potential. So what happens when you compare or share two capacitors? When we share two capacitors, charge flows until they acquire same potential. Same potential. And this is the common potential. Just note it down. Then we'll calculate the loss in energy.
So finish.
Okay. Now, after this charge, you can calculate there's some loss of energy. See, what's the cause of loss of energy? When charge flows in a circuit, then the flow of charge is current. Due to the flow of charge, some current is flowing through the circuit. When current flows through the circuit, then a part of electrical energy get dissipated as heat. These wires will get heated up. Due to the flow of current, these wires get heated up. Means you will have some heat energy. What is the source of that heat energy? Heat energy? A part of electrical energy get converted into heat energy. This heat and electrical energy C1V1 square. This electrical energy half C2V2 square. A part of this energy get converted into heat energy. So you're supposed to calculate that heat energy. You're supposed to calculate that heat energy. A part of energy get converted into heat energy. So next you have to calculate the loss energy. Energy before shearing is not equal to energy after shearing. Okay, just note down this coming in one. Yeah, sorry. Loss in energy. So there is some initial energy stored in capacitor 1, then there is energy stored in capacitor 2, there is some energy in the final system. The energy in the final system is less than the energy in the initial system. A part of energy of the initial system get dissipated as heat. We have to calculate that loss in energy. So we write loss in energy as delta U, which is initial energy minus final. Say, how much is initial energy? That's half C1 V1 square. That's energy stored in first capacitor. Plus half C2 V2 square. This is the energy stored in second capacitor. When we calculate final energy, so Ahmed, what is the energy stored in this capacitor? Yes,
C1,
how much?
C1, V1.
This is half C1 V square, and in the second capacitor is half
Of C2 is square.
So the loss in energy is half C1 V1 square plus half C2 V2 square. It's minus half V square C1 plus C. V square C1 plus C. Next, what we can do is we can substitute the value of this V. How much is this V? This V is common potential, which is C1 V1 plus C2 V2 divided by C1 plus C. When we substitute these values, what I get is delta U, which is half C1 V1 square plus half C2 V2 square minus half C1 plus C2 V square, and V is this C1 V1 plus C2 V2 over C1 plus C2 whole square. Next, we can write this as delta U, which is half C1 V1 square plus half C2 V2 square minus half C1 plus C2. We can further write this as C1 square, or we can write this as C1 V1.
Sir,
Yes,
so we can cancel that C1 plus C2, right?
yes, I'm cancelling it. Over C1 plus C2 whole square. So this C1 plus C2 will cancel this whole square. Next, lengthy calculation. Next, we can take this half C1 C2 as LCM. So it will be 2 C1 plus C2 as LCM. This is C1 V1 square. C1 V1 square into C1 plus C2 plus C2 V2 square into C1 plus C2 minus C1 V1 plus C2 V2 whole square minus C1 V1 plus C2 V2 whole square. So this delta U is, you can multiply it here. So that will be C1 square V1 square plus C1 C2 V1 square. You multiply it here. So this is C1 C2 V2 square. You multiply it here. This is C2 square V2 square. Then you can open this whole square. You will be left with C1 square V1 square minus C2 square V2 square minus twice of C1 C2 V1 V2 divided by twice of C1 plus C2. So C1 square V1 square will cancel this thing. C2 square V2 square will cancel this thing. So you will write delta U is C1 C2, it's V1 square plus V2 square minus 2V1 V2 by 2 C1 plus C2. So this is C1 C2 over twice of C1 plus C2 into V1 minus V2 square. So this is the expression for loss in energy. So this is loss in energy when you connect two capacitors, C1 C2 V1 minus V2 square over twice of C1 plus C2. Just one more thing. This expression is valid for both capacitor as well as conductor. Whether you share two capacitors or you share two conductors, physics will be same. When you share two conductors, then again charge will flow from one conductor at higher potential to another at lower potential until they acquire same potential. So flow of charge or the sharing of two capacitor or sharing of two conductors are the same. Just note it down and tell me once you have written this thing. Just note it down.
Sir.
Yes. Yes, written.
Yes, sir.
Yes, written.
Yes, sir.
Okay, solve this simple number, or at least solve at least one numerical today. Huh? It's a single formula based numerical. This is one capacitor. The capacity is, say, 10 farad. The potential difference across the ends of capacitor is 20 volt. So this is your C1 and this is your V1. A capacitor of 10, I write this as picofarad, because in school exams you will not get farad, you will get picofarad, is connected charge to potential difference of 20 volt is connected to an identical but uncharged capacitor C2. Calculate first part. Common potential, second part. Loss in energy on sharing. This is a formula based numerical. Please solve at least this numerical. 1 picofarad is 10 to the power minus 12 farad. This is how we convert picofarad to farad. Do it. Not C2 will be 0, V2 will be 0. V2 will be 0. Capacity is same, V2 will be 0. Ahmed, you're supposed to calculate V. See, C2 is same, na? It's connected to an identical capacitor C2. C2 is identical. If C1 is 10 picofarad, then C2 is also 10 picofarad. V2 is 0. You're supposed to calculate V.
Okay, sir.
See, yes, no, you're correct. See, there is no point in completing the syllabus if you cannot solve basic numericals like this. Yes, Ahmed, you're correct. Abdullah, Malia, Mariam, answers. Shazada. Okay. Say C1 is 10 picofarad. You can write this as 10 into 10 raised to the power minus 12, 10 raised to the power minus 11 farad. Then you have C2, which is also identical, 10 picofarad. So that's 10 into 10 raised to the power minus 11 farad. V1 is 20 volt. V2 is 0. You're supposed to calculate V. Amalia, is it? V2 is 0. You're supposed to calculate V, common potential. We calculate common potential in this way: C1 V1 plus C2 V2 over C1 plus C2. When we substitute values, C1 is 10 raised to the power minus 11. V1 is 20. Yes, Amalia, now you are correct. V2 is 0. C1 is 10 raised power minus 11. C2 is 10 raised power minus 11. So this is your common potential. It's 20 into 10 raised to the power minus 11. 10 raised to the power minus 11 plus 10 raised power minus 11. It's 2 into 10 raised to the power minus 11. Gets cancelled out. So this is your V. V becomes 10 volt. So this is the common potential, which is 10 volt. So when we connect two capacitors, then the charge flows from one capacitor to another and the common potential comes out to be 10 volt. In the second part, you have to calculate loss in energy. For loss in energy, use this direct relation C1 C2 V1 minus V2 square over twice of C1 plus C2. Substitute all the values C1 C2 V1 V2 and get the value of delta U. Calculate how much loss in energy is coming. Okay. Well, I think you are not doing unit conversion. You're ignoring unit conversion. C1 and C2 are 10 raised power minus 11 farad, not 10. Ahmed, Shahzada, Abdullah, Amalia.
Z1.
Yes, sir, one thing.
You just have to substitute the values of C1, C2, V1, V2. That's it. Okay, Abdullah. We'll check. Shahzada, you're not also, I think you're not even doing unit conversion. You're taking it 10 raised power minus 11 farad. Just like Noor, you are taking it 10. Okay, Amalia. It's okay.
10 raised to minus
I think
9.
Amalia is correct. See, when I substitute all values, yes, now you are correct. Ahmed and Noor, I think now you are correct. Delta U is C1, C2. It's V1 minus V2 square over twice of C1 plus C2. C1, C2. C1 is 10 raised to the power minus 11. C2 is 10 raised to the power minus 11. V1 is 20. V2 is 0 square. divided by twice of 10 raised to the power minus 11. 10 raised to the power minus 11. So that is 10 raised to the power minus 22. 20 square is 400. Divided by 2 into, this will be 2 into 10 raised to the power minus 11. So this is 4, this gets cancelled out, this is 100. So this will be 10 raised to the power minus 9. This is the loss in energy. Amalia, you're making some mistake in calculations. Is it clear now? Abdullah, not 2. It will be just 10 raised power minus 9.
Yes, sir. Done.
Shahzada, you get this answer now?
Yes, sir.
Sorry. Solve one more question. This is another question given in CRT on the same.
Yes, sir.
Now, instead of capacitor, you have spheres. Just note it down and tell me once you have it.
Sir, done.
Answer.
In next numerical, instead of capacitor, 2 spheres are given. So you have 2 spheres. Have different radii. Radius is R1. Charge on the surface of this sphere is Q. Radius is R2. Charge on the surface of this sphere is Q. These are initial charges. When you connect these 2 spheres, then charge flows from one sphere to another. And let's say initial charges are not given. So you have 2 spheres, one of radius R1, another of radius R2. You connect these 2 spheres. Yes, Abdullah. What happens when you connect 2 spheres? Consider these spheres like a conductor. Yes, Abdullah. What will happen when you connect 2 spheres?
Charges flow from one.
Charge flow from one sphere at higher potential to another sphere at lower potential until they acquire same potential. So when you connect these 2 spheres, then charge will flow from one sphere to another. And the flow of charge will stop only if both the spheres are at same potential. One have, but charge may be different. One have charge Q1, another have a charge Q. So 2 conducting spheres are connected calculate first one. Ratio of charge on 2 spheres second, their surface charge densities. Third one. Let's say their electric field. See, solution. When you connect these 2 capacitors, then or 2 conductors, then which quantity will remain same? When we connect 2 capacitors, then out of charge, capacity, and potential
difference.
potential will be same. So you can say potential of first sphere is equal to potential of second sphere. Potential of first sphere will be equal to potential of second sphere. So potential of first sphere is Q1 over 4 pi epsilon naught R1 second sphere is Q2 over 4 pi epsilon naught R. 4 pi epsilon naught will cancel this 4 pi epsilon naught, and you will get Q1 by Q2 ratio of charges R1 by R. So these are the ratio of charges of these R1 by R. Yes, is it clear?
Yes, sir.
Yes, sir.
Now you need next second and third part you will solve. I'm writing the formula. If you forgot the formula, then I'm writing the formula. Surface charge density is charge upon area. If you forget the area of sphere, then I'm writing the formula for the area of sphere also, 4 pi r square. Get the ratio of sigma. Do it now. I need the ratio of sigma 1 by sigma 2.
So we just have to find the ratio.
Surface charge density, sigma 1 and sigma 2. This is surface charge density.
So we have to find ratio of this, just sigma.
Ratio.
So finish.
No, I think you're making some mistake. Abdullah is correct. No, Malia, you're also making some mistake. You cannot ignore the right hand side. Okay, I'm solving it. See, the ratio of Q1 and Q2 that I get is R1 by R2. Huh? Q1 by Q2 is R1 by R2. No, Ahmed. I need sigma 1. Sigma 1 is Q1 by its area. So I'm doing one thing. See, I'm dividing Q1 by 4 pi R1 square. And I'm also dividing Q2 by 4 pi R2 square. The rule of equation, if I'm dividing left hand side with 4 pi R1 square, then I should also divide right hand side with 4 pi R1 square. Similarly, this with 4 pi R2 square. This is the rule of equation. If I'm dividing on the left hand side, then I should divide on the right hand side also. Is this a step clear? Noor, Malia?
Yes, sir.
This Q by 4 pi R1 square, this is sigma 1. This Q2 by 4 pi R2 square, this is sigma 2. This 4 pi will cancel this 4 pi. R1 will cancel the square. R2 will cancel the square. R2 will move to numerator. So sigma 1 by sigma 2 is R2 by R2. That's the ratio. Sigma 1 by sigma 2 is R2 divided by R. That's equation number. Third equation. Electric field. E1 by E2 is sigma by epsilon. E1 is sigma 1 by epsilon. E2 is sigma 2 by epsilon. So epsilon naught will get cancelled out with the epsilon naught. So the ratio of electric field is same as that of surface charge density, which is R2 over R. Note it down. That's the ratio of surface charge density, and this is the ratio of field also. On the surface of a conductor, field is sigma by epsilon. Yes. Written?
Yes, sir.
Okay, I will stop today a bit early. I'm I'm ending the class now. Maybe on Wednesday I will take one more class. I will ask chemistry teacher to give me that lecture. Noor, you have your Quran classes from what time? Noor? Noor, what are the timings of your Quran classes on Wednesday? Noor is not in class. Anyways, I'll stop here. From next class that I will try to take on Wednesday, I will continue with electric circuit. So
Okay, sir.
we'll be starting with circuits of capacitor as well as resistor. Okay, so let's stop here.
Thank you, sir.
And
Thank
please
you.
revise. Please revise.
Thank you, sir.